amazing new paper shows everything wrong with LLMs and when they can and cannot reason and generalize, and do they actually reason or are they just matching patterns. It helped me understand so well. So first I will just summarize for you in 1 minute and then we will go into deep dive, which will also be very interesting. So they show 3 types of generalization. The first type of generalization: if you train LLM with reinforcement learning to solve some task, then you test it on a bit more difficult tasks that were not in the training data. It shows that it can actually generalize to a bit more difficult tasks. Not a lot more difficult, but a bit more difficult, but same type of tasks that require like a specific skill. For example, a question: what if you have some letters, how can you arrange them in this and this way? So if you make later the task more difficult, more letters or more ways, even though it wasn't trained on such difficult tasks, it can generalize if the task is a bit more difficult, but not too much. So LLMs can generalize a little bit in that way. And then second type is if you have 2 unrelated skills. Let's say one is about some geometry type of task and the other is about arranging stuff, skill B. So if you take reinforcement learning and train LLM just on that geometry kind of task and separately just on that other skill, like arranging some stuff, and then later you make a task that requires both of the skills, it actually is not so good at combining both skills to solve the task. And keep in mind that it was not trained to combine those 2 skills. It was just trained to be good at those skills separately. So each training data point just had one of the skills, and it was trained on just one of the skills, because it wasn't trained to combine them. And you see that happens all the time. So this is the second type of generalization that it's not really good at, or very little. We see some improvement here, we see some improvement here, but a lot less. So the third type of generalization is if you train the model to solve, let's say, polynomial division, this example, it will become better at solving that. But if we also have polynomial division with just different numbers, then maybe this strategy that it learned in reinforcement learning is not best for this type of polynomials. Maybe in the training it was just learning to solve 2nd and 3rd degree polynomials, but in testing 5th degree polynomial, you should use different strategy. But it shows here that it just applied this strategy for 2nd and 3rd onto the 5th as well, which actually caused degradation after the training. This is a problem because you see here, before reinforcement learning, it was even applying those different strategies. But after reinforcement learning, it started just applying this same strategy. And in this case, it caused degradation in performance because that was not correct strategy for this task, even though the task is also polynomial division and it's very similar looking. It's seemingly similar. So completely fails on the third type of generalization, where for similar looking tasks, it needs to come up with different novel maybe ideas. So it just, after reinforcement learning, just whatever it learns, it applies to every similar task. You see here no improvement, and this a bit of improvement here, and this is a degradation. So this type of out-of-box novel ideas, this paper shows that it fails at that. So now let's go into the deep dive of the paper. So it's made to not to be present in the training data, where the tasks force the LLM to think outside of the box, where it cannot just retrieve the answer from training data. The authors argue that while top-tier LLMs perform well on standard math benchmarks, They often rely on narrow set of learned strategies and fail when novel thinking is required. So top LLMs have already learned narrow set of reasoning, problem-solving abilities, and when a new ability, new way is required, they fail. And also, like the new Gemini 2.5 Pro is just the best. Like it's end of story best. Like for me, it's just the best. So they create these three categories: exploratory generalization, applying a known problem-solving skill to more complex instances of the same problem type. For example, extending a geometry problem from an octagon to a more complex dodecagon. Compositional generalization, combining multiple distinct skills which were learned in isolation to solve a new problem that requires their integration. For example, using both polynomial factorization and integer GCD methods, whatever that means, to find the GCD of two polynomials. Greatest common divisor, okay. Transformative generalization, abandoning a familiar but inefficient strategy in favor of a novel, more efficient one, switching from brute force enumeration to a clever, subtractive counting method. As an example, Omega consists of programmatically generated training and test problem pairs across 6 mathematical domains: geometry, number theory, algebra, etc., with solutions verified by symbolic, numerical, or graphical methods. This control generation allows for precise isolation of each reasoning capability. Key findings. Frontier models struggle with complexity. When evaluating leading LLMs like DeepSeek R1, Claude, and O4 Mini, I guess they don't have O4. The study found a sharp performance degradation as problem complexity increased, even on simple extrapolatory tasks. Model often discovered correct solutions early, but then overthought their way to incorrect answers or got stuck in error spirals. So I think this portrays the problems that we all feel that LLMs have. They rely too much on memorization, even memorizing the algorithm of solving the problem, and they cannot generalize enough, even nearly like humans. Even though the LLM progress in the last 5 years has been good, they still lack this generalization capability that humans have. Even though, as I said before, even human intelligence is very narrow. We only know well how to move around and maybe read other humans' emotions and plan a little bit. But LLMs seem to be even more narrow. Reinforcement learning generalization limits. The authors fine-tune Quen's series model using reinforcement learning on Omega's training set. Exploratory. Reinforcement learning led to notable improvements, successfully generalizing from easier to harder problems within the same domain. Okay, within the same domain, so still a bit narrow. Compositional. Generalization was very limited. Even after mastering individual skills, models struggle to combine them effectively to solve composite problems. I think this could be solved with better AI algorithms. Transformative. There was little to no improvement. Reinforcement learning reinforced familiar strategies but failed to introduce the creative leap needed to discover new, unconventional solution paths. Actually, usually reinforcement learning has higher creativity than other things, because other types of training, because it's randomly trying out different stuff. But I guess reinforcement learning is not good because rewards are too sparse and too far in between. So I don't know if reinforcement learning is the way. Maybe scaling compute or making it more efficient, or maybe energy models as opposed to reinforcement learning, or some other architecture or algorithm. Omega benchmark reveals a critical gap between the mechanical proficiency of current LLMs and genuine mathematical creativity. While models can be trained to extend known methods, exploratory reasoning, they largely fail at integrating skills compositional and discovering novel approaches transformative. The paper concludes that simply scaling models or data may not be enough, and the Omega provides a crucial tool for diagnosing these fine-grained failures and guiding future research towards more robust and creative AI reasoners. I think there are ideas on how to fix this. We just need to try these ideas and build those models and do research, which takes some time because you need to code everything and do research and stuff. But even I have some ideas about more general models, like combining video and text pre-training, fully combining, not just attaching two different video encoder and text encoder, but actually combining it from scratch and training on the same transformer, same attention. So that, for example, could increase data a lot to the LLM or the large model, whatever it is, large video model maybe or something, and maybe make it smarter, more intelligent, and maybe more intelligent means like more generalizable, maybe more creative as well. I guess these labs like Google and OpenAI are probably trying these things out right now as we speak. The results strongly suggest that current LLMs are phenomenal pattern matchers and produce procedure executors, but they are not yet flexible, creative reasoners like humans. They learn specific solution shapes rather than abstract mathematical principles. That's crazy, that's interesting, rather than abstract mathematical. So what are these and how do we train AI to get these? I guess abstraction, I'm not sure, I don't know. Would it have to do with JEPA models by Jan LeCun? Maybe predicting the abstracted video, but I don't know. The paper argues that simply throwing more data and more compute at the problem, brute force, won't solve these fundamental generalization issues. An LLM trained on a trillion examples of peeling garlic by hand will never discover the shake it in a jar method. So Omega provides a diagnostic tool. Researchers can use it to see where their model fails. So the author suggests ideas like curriculum scaffolding, intelligently structuring training data to first teach basic skills, then compositions, and finally transformative problems. Yes. I guess we just need to create mathematical data for this. I'm gonna think about this further. I think it would be maybe too difficult for me alone, or maybe not, or maybe I can do some videos and help somebody, or I don't know. Meta reasoning. Building models that can reason about their own reasoning. Yo, that's crazy. A model that can recognize this brute force approach is taking too long. I should try something else. Would be a huge leap forward. Yeah. Let's now take a look at specific task examples from the paper and analyze how model performed on them. So, exploratory generalization, scaling a known skill. Task example, letter distribution from combinatorics. So this is the first problem. You have these letters. You have Z 3 times, L 4 times, K 1 time, and W 4 times. Total 12 letters. And you have 4 boxes with capacities 2 letters, 3 letters, 2 letters, and 5 letters. So in each box, there can fit this corresponding amount of letters. Goal: count how many different ways to assign all 12 letters into the 4 boxes such that box 1 holds 2 letters, box 2 holds 3 letters, etc. Identical boxes means same arrangement in two boxes equals same outcome. So that means groupings like ABC and CAB are not distinct, so they are same. So the order of letters doesn't matter. It just matters how many, like which letters are in the box. Letter counts must be respected, so only 3 letters Z. So this same thing is explained here, just like in a different way if you want to read. So that was the simple task. That's simple. This is quite hard, even the simple one. But the high complexity one, it's different. We have 14 letters and 5 boxes. It's same rules, just more complex, more letters and stuff. So I'm not sure I 100% get the rules even, especially solving the task. So why is it difficult for LLMs? Even humans struggle to do this without code. There is a combinatorial explosion in possibilities. It's especially hard for language models to handle indistinguishability both of letters and boxes. So, if you just swap same letter from different boxes, you actually did not make any change. And then let's see how models performed. So frontier LLMs, figure 7. This is where we see the dramatic performance drop. The pass at K metric shows how many attempts K it takes for the model to find the correct answer. Here we have the figures. So these 2 questions that I showed you are just complexity level 5 and 6, but there are other from 1 to 4 complexity levels. So we have OpenAI O4 Mini, O3 Mini, R1 and 3.7 Sonnet. And complexity level 1 seems very simple. So we see that first try they don't get it completely, but actually this is second try, they get it almost completely, so O3 Mini gets it. Yeah. And then complexity level 2, O3 Mini is actually very low. That's surprising. Why is O3 Mini so much lower than R1, for example? I don't think it should be. So O3 Mini, even after 32 attempts, just gets 80% of the result correct. O4 Mini seems really good at this. You see how it's getting 100% at level 3, where these ones don't actually. So O3 Mini, okay, so R1 is getting a lower score at level 4 than O3 Mini. I would say this then means that maybe R1 data, training data is different than O3 Mini. So actually O3 Mini keeps now being best besides O4 Mini. And it looks like it's due to training data. But level 6, all of them collapse. No results. Maybe they get a little bit of results here. This is so interesting to see. I think this paper is really good. I think it tries to demystify more about LLMs just memorizing and how much they generalize. I guess O4 is trained, so O4 scores better results. Now, is it trained on more data? Does it actually generalize more, or is it just memorizing more patterns? I'm not sure. But we can look at the results of other tasks, and if all of them are consistently good for O4 Mini, which I think they say that this one is best, maybe others are not so good. We'll see. I must say though, LLMs are surprisingly useful, especially in explaining this paper, for example. So even though I'm saying like no generalization and stuff, I really like Gemini Pro. It's so good, it's so helpful. So I think they are surprisingly useful and surprisingly good. especially at explaining stuff, even though they can't maybe generalize too much. Keep in mind that just you see letters 12, letters 14, but there is a lot more possible arrangements if you have letters 14. It's not just a bit more, it's a lot more. The growth is, I don't know if it's exponential or quadratic or something, but it's very fast. So LLMs are not able to keep track in their, like, mentally keep track of all of the letters and stuff. And authors say that they do have enough context window, so it's not context window running out, it's just that it's too much stuff going on, too many arrangements. Then they trained Qwen 2.57b instruct on this Omega dataset to try to improve its performance. Actually, there is some generalization. So when they fine-tuned or trained this model with reinforcement learning on this Omega dataset, they tested on the same task difficulty as in this training data and on different task difficulty or different types of task. So the blue lines represent, so the dark blue is the performance on before it was trained on this data that it was trained on, and dark orange is before it was trained but on data that it will not be trained on, so out of distribution. So the blue is about data that they trained on, and the orange is testing on data that it wasn't trained with reinforcement learning by them to test if it generalizes to the out of distribution data. And the light blue is the improvement after reinforcement fine-tuning on the in distribution data. And the light orange is how much it improves on out of distribution on data that it didn't train on. So we actually can see that it does improve on out of distribution data as well. Here in geometry there is no improvement. What is this? So okay, so before it was 0 and maybe +8 after. So yeah, there is improvement in geometry as well. But you see, improvement in some of them is a lot smaller, like in geometry. So the improvement here is just on the data that's similar to what it's been fine-tuned on. But in some places we also see big improvements on out of distribution data. Reinforcement learning yields strong improvements across most domains on in-distribution tasks. However, gains on out-of-distribution tasks that are not so similar as the training reinforcement learning data, are typically lower and more variable, highlighting the limits of generalization from scene distributions. But you see, it's still unclear, so it looks like it does generalize a little bit, but it's unpredictable and variable. But it does generalize, so I'm not sure. So I think these are positive, these are good results. I didn't even expect them to generalize so well, look. And I believe these tests are done properly, so actually this is surprisingly good in my opinion. So this figure 8 just shows training was done on level 1 and level 2 that we described earlier, and the out of distribution was the level 3. So they didn't go beyond level 3. So this figure is about our example that we were discussing earlier, that I said that maybe this is the easiest, the best type of example for the LLM, and we need to now see other types of examples that are not so, that LLM may not perform so well on, and may not generalize or learn about so well. Compositional generalization, integrating two skills. Can reinforcement learning learn to compose math skills into integrated solutions? Strong performance on isolated skills but limited compositional generalization is what this shows. So we have this skill A and skill B, and let's see what those are. Skill A is understanding the geometric properties of our regular polygons, diagonals, and rotational symmetry. For example, in a regular octagon, draw diagonals from 5 to 3 and 2 to 7, rotate the figure and overlap it. How many small triangles are formed? This tests spatial and geometric reasoning. This is hard for me, I swear. What is this so difficult? Skill B, counting arrangements or patterns in a structured set. Example, from the multiset Y2F3G1, what is the expected number of matches of the pattern F, and then this asterisk F? So I guess it can fit anything instead of this asterisk. I'm not sure exactly what this asterisk mean. So, and then we have compositional test problem. So it combines two of them. Find the number of rectangles that can be formed inside a fixed regular dodecagon, where each side of the rectangle lies on a side of a diagonal of the dodecagon. So this compositional test problem requires both skill A, geometry and rotation, and skill B, combinatorial pattern matching and stuff. So it will test for combination, how well LLM can combine those two skills. So here we have different tasks for skill A. So we have circle, we have probability is not fixed, we have polygon color, I don't know what there is, maybe it's explained here, but geometry. And we see, if we just look at dark blue, this is before reinforcement learning, it kind of performs low, and after reinforcement learning it performs strongly on this skill. So the reinforcement learning is done only on a task that require one of these skills. So on separate tasks, only tasks that just require skill A. So after this reinforcement learning, you see we have improvement in this skill, or it only tasks with only skill B. So you see big improvement on skill B for each of these types of skill B. But you see that there is no improvement here on the tasks that require generalized both of the skills together to solve. And they did not train on any tasks that require both skills to solve. So they just tried training on individual and see how model can combine, and here it cannot combine. So here there is some improvement, but you see improvement here is huge, and here is even bigger than this. And here there is no improvement at all. And here a bit of improvement, and here there is some improvement, and there is no improvement. So this says that even though LLM learns to perform these tasks better individually, if it's not trained to use them in combination, it will not increase or become better a lot. So in the first type of tasks that I explained earlier, we just had difficulty increase when we are testing out of distribution, and it generalized a bit, or maybe even a bit more. But here, where it needs to combine two different learned tasks, there is a lot less generalization. Third type is transformative generalization, finding a clever new strategy. So here they used this task of dividing a cubic or quadratic polynomial using a rational root theorem. So here you just list all possible rational roots, p given this q, p over q. So p is the polynomial, q is the root, and then you divide each one and see which ones it's gonna give you, I think 0 equals 0 or something like that. But if you get like 1 equals 0 or something, then it's not the correct solution. It's not the root that it's divisible by. So it's been trained on that. So they trained on this type of examples, but then in the testing, they're gonna give some example that will require different strategy. And they want to see if it will use the same strategy, which would be impossible or too difficult to solve with, or it will figure out this new strategy. So they give a quintic polynomial x to 5, while the training was just done on x squared or x to 3. And here it will be too difficult or maybe too slow or maybe impossible, I'm not sure, to use root theorem. So it says it's very unlikely to work. However, by noticing its structure, a clever mathematician might try a substitution like x is equal to t plus a over t. This is a non-obvious out-of-box insight. So let's see the performance of the model on this figure 11. I will explain. Let's first read here. The base model had some small non-zero accuracy on the out-of-distribution tasks. So these are ones that require different methods. Perhaps from seeing similar tricks in its pre-training data. It had around 20% accuracy on the in-distribution standard problems that it was fine-tuned on with reinforcement learning by the Allen AI team. So what happens in more detail is after reinforcement learning, the stuff it was trained on performance got from 20% to 62%, big boost. The model became excellent at applying rational root theorem. It mastered the familiar strategy. Conclusion: the reinforcement learning process heavily reinforces the familiar brute force strategy, or whatever the familiar strategy is. Because that strategy was rewarded over and over, the model becomes more likely to try it, even on problems where it was doomed to fail. It never learned to recognize, this strategy isn't working, I need a new idea. It failed completely at transformative generalization, so yeah, this one completely failed. They say this shows that current reinforcement learning methods are good at optimization, but poor at genuine exploration of novel solution spaces. This is exactly what I understood from previous papers. It's good if model already knows the correct answer, or if it's able to apply it. So reinforcement learning will just make a model more familiar how to apply that answer correctly and quickly. But reinforcement learning seems not to be able to discover new things in a way that we are training it, at least. I think it's happening because LLM, there is too many tokens and there is too much possible stuff. I think our reinforcement learning algorithms or training is way too small compared to the size of possible combinations of all tokens and stuff. So reinforcement learning usually has creativity, but I think the task of exploring it, getting these new solutions, is too difficult for the current training stack. So either we will have to scale or probably come up with better algorithms or optimizations to train more with reinforcement learning. And this is funny. So before reinforcement learning, on in distribution 19, out of distribution 70. But after reinforcement learning, it improved on this what it was trained on, but degraded on this out of distribution. So I guess it learned to just apply this strategy now, and that strategy was not good for this out of distribution task. So now it was applying this new strategy that helped it during training onto everything, which made performance go down. And in these cases, it improved a lot on in distribution, but did not learn to come up with new things. I think this experiment shows the fundamental limitation of large language models. So they cannot actually generalize so well, even though they can make these big improvements in what they are trained on. So I think architectures and maybe training on video merged with text, not just Frankenstein video and text, but merged from scratch using same architecture, that could maybe cause generalization, but that's just my guess. So the whole pre-training like that. And here there is a bit of improvement, but it shows that in this experiment it's performing very poorly. So let's summarize. The first experiment was about training on a specific task and then just decreasing difficulty a little bit, and it performed well if the difficulty is increased a bit but the task is the same. Second experiment was training two separate skills and was tested on how well it can combine those two skills, and not so well. It can just use skills individually, well, because it was trained to use skills individually, but not combining them. And the third task, where it needed to completely invent new strategies, actually performance got even worse than before reinforcement learning training, because it just learned one strategy during the reinforcement learning training and then it tried to apply everywhere, even though without that reinforcement learning training it would have been applying more appropriate strategies, not just wouldn't be so biased for that one strategy. So this one failed miserably because it was trying to test if it can come up with new appropriate strategies. Check out my channel for more videos, and see you next time.